Welcome to DAR Tutors. Today, we're delving into a fundamental concept in higher-level chemistry: how far a chemical reaction proceeds. Specifically, we'll be discussing the reaction quotient and its profound relationship with the equilibrium state. Our main objectives today are to define the reaction quotient Q and show how to calculate it for any reversible reaction. You will learn to use Q to predict the direction a reaction will take to reach equilibrium, and you will see how it helps explain Le Chatelier's principle. By the end of this session, you will be able to perform calculations using initial and equilibrium concentrations to determine equilibrium constants or unknown equilibrium concentrations. Let's start with the basics. A reaction quotient Q is a value that helps us understand the current state of a reversible reaction relative to its equilibrium state. For a general reversible reaction like AA plus BB is in equilibrium with CC plus DD, where the lowercase letters are the stoichiometric coefficients, the reaction quotient is defined as the concentration of products raised to their coefficients, divided by the concentration of reactants raised to their coefficients. This formula might look very familiar, as it's the exact same mathematical expression as the equilibrium constant K. However, there's a critical difference. The equilibrium constant K is calculated only at equilibrium, meaning the concentrations used are the equilibrium concentrations. For a given temperature, K has a fixed single value. In contrast, the reaction quotient, Q, can be calculated using the concentrations of reactants and products at any point in the reaction, not just at equilibrium. As a reaction proceeds, Q changes. Only when the system reaches equilibrium does the value of Q become equal to K. In summary, Q can be calculated at any time using any concentrations, while K is a constant value calculated only at equilibrium concentrations for a specific temperature. Let's repeat that. Q is a variable that can be found at any point in a reaction's progress, while K is a constant that applies only when the system is at equilibrium. Now, the real power of the reaction quotient lies in its ability to predict the direction a reaction will shift to reach equilibrium. By comparing the calculated value of Q with the known equilibrium constant K, we can determine if the reaction needs to make more products or more reactants. Let's visualize this with a graph. Consider a simple equilibrium between reactant A and product B, with an equilibrium constant K of 1.5. The horizontal red line represents the fixed value of K. The blue curve represents Q, which varies with the composition of the mixture. As we move from left to right, we have more products and fewer reactants, so the value of Q increases. There are three possible outcomes. First, if the value of Q is less than K, this means the system has a lower ratio of products to reactants than it would at equilibrium. To increase this ratio and reach equilibrium, the reaction must proceed in the forward direction, creating more products and consuming reactants. We say the reaction shifts to the right. Second, if Q equals K, the system is perfectly balanced. The ratio of products to reactants is the same as the equilibrium constant. The reaction is at equilibrium, and there is no net change in the concentrations. Third, if Q is greater than K, the system has a higher ratio of products to reactants than at equilibrium. To restore balance, the reaction must proceed in the reverse direction, consuming products and creating reactants. The reaction shifts to the left. A simple way to remember this is that Q always seeks to become equal to K. It's a journey towards balance. Now let's see how the reaction quotient can help us explain a fundamental principle you've learned before: Le Chatelier's principle. This principle states that if a dynamic equilibrium is disturbed by changing the conditions, the position of equilibrium shifts to counteract the change. Let's use the Haber process as an example. Nitrogen gas plus 3 moles of hydrogen gas are in equilibrium with 2 moles of ammonia gas. At equilibrium, Q equals K. Now, what happens if we disturb this equilibrium? Let's say we increase the concentration of one of the reactants, hydrogen gas. The system is no longer at equilibrium. First, we write the expression for the reaction quotient. When we add more hydrogen gas, the value of the denominator in the Q expression increases. This causes the overall value of Q to decrease. It is now less than K. Since Q is now less than K, we know the system will shift to the right, towards the products, to re-establish equilibrium. This means it will produce more ammonia. This is exactly what Le Chatelier's principle predicts. By adding a reactant, the system shifts to consume it and produce more products. So we can see that the reaction quotient provides the mathematical justification for Le Chatelier's principle. It shows us how a change in conditions changes Q, which then drives the reaction to shift in a direction that restores Q to the value of K. Now let's turn our attention to the quantitative aspect. Calculating equilibrium constants. We can easily calculate K if we know the equilibrium concentrations of all reactants and products. Let's work through an example. Nitrosyl chloride, NOCl, can dissociate into nitric oxide, NO, and chlorine gas, CCl2. We have the equilibrium 2NOCl in equilibrium with 2NO plus Cl2. At 503 K, the equilibrium concentrations are NOCl, it's 2.33 T 10 to 3 m NO equal 146 pisky to 10 3 m Cl2 equal 1.asbmati to 2 tens. We are given the equilibrium concentrations at a specific temperature, 503 Kelvin. Our first step, part A, is to write the expression for the equilibrium constant K. The equilibrium expression is products over reactants. So, K equals the concentration of NO, squared due to the coefficient 2, times the concentration of Cl2 to the power of 1, divided by the concentration of NOCl squared. Part B asks us to calculate the value of K at 503 Kelvin. We simply substitute the given equilibrium concentrations into our expression. This gives K equals 1.46 times 10 to the minus 3 squared, times 1.155 times 10 to the minus 2, all divided by 2.33 times 10 to the minus 3 squared. Performing this calculation gives us a value for K of approximately 4.5 times 10 to the minus 3. And that's how you calculate the equilibrium constant from equilibrium concentrations. You write the expression and substitute the values. Let's extend our worked example to include another temperature, 738 Kelvin. This will allow us to investigate the energy change of the reaction. At this higher temperature, the equilibrium concentrations are different. NOCl is 3.68 times 10 to the minus 4 molar. NO is 7.63 times 10 to the minus 3 molar. And Cl2 is 2.14 times 10 to the minus 4 molar. We use the same expression for K. Substituting these new values, we get K equals 7.63 times 10 to the minus 3 squared, times 2.144 times 10 to the minus 4, all divided by 3.68 times 10 to the minus 4 squared. The calculation yields a value for K of 9.2 times 10 to the minus 2. Now for part C, we compare our two K values. At the lower temperature of 503 K, K is small. At the higher temperature of 738 K, K is larger. This means K has increased with increasing temperature. An increase in K indicates that the forward reaction is favored at higher temperatures. A larger K means the ratio of products to reactants is greater at equilibrium. Following Le Chatelier's principle, if increasing the temperature favors the forward reaction, that reaction must be endothermic. It absorbs the added heat to counteract the change. So, by calculating K at different temperatures and observing the trend, we can determine the nature of the reaction's enthalpy change. Here, K increasing with temperature tells us the forward reaction is endothermic. Often, we don't know all the equilibrium concentrations. In these cases, we use a powerful tool called an ICE table to organize our data and solve for the unknowns. ICE stands for Initial, Change, and Equilibrium. This table helps us track the concentrations or amounts of reactants and products as they evolve from initial conditions to equilibrium. Let's consider a simple example. The equilibrium between substance A and 2B. Suppose we start with 1 mole of A and 0 moles of B in a 1dm3 vessel. We find that at equilibrium, the amount of A is 0.75 moles. We can build our ICE table. Initially, we have 1 moles of A and 0.0 moles of B. At equilibrium, we have 0.75 moles of A. To get from an initial of 1 T to an equilibrium of 0.75, the change in A must have been a decrease of 0.25 moles. We write this as 0.25 in the change row for A. Now, we use the stoichiometry of the balanced equation. For every 1 mole of A that reacts, 2 moles of B are produced. So, if we had a change of 0.25 moles of A, The change in B must be 2 times that, or plus 0.50 moles. We add plus 0.50 to the change row for B. Then we find the equilibrium amount of B by adding its initial and change values. 0.0 plus 0.50 equals 0.5 moles. Now we have the equilibrium amounts for both A and B. Since the volume is 1 dm3, these amounts are also the concentrations in mole dm3. We can calculate K. The expression is K equals concentration of B squared over concentration of A. Substituting our equilibrium values gives K equals 0.55 squared divided by 0.75, which equals 0.33. This example shows how an ICE table allows us to deduce all equilibrium concentrations from a single known value and the stoichiometry, which is crucial for many problems. Let's work through another ICE table problem, this time calculating K for the Haber process. The problem states that 1 mole of nitrogen and 2 moles of hydrogen are placed in a 2 cubed vessel. At equilibrium, 0.4 moles of nitrogen remain. First, we need to convert amounts in moles to concentrations. Since the volume is not 1 dm cubed, the initial concentration of N2 is 1.0 mole divided by 2.0 dm cubed, which is 0.50 m. For H2, it's 2.0 mole divided by 2.0 dm cubed, which is 1.0 m. At equilibrium, the concentration of N2 is 0.4 mole divided by 2.0 dm cubed, which is 0.2 m. Now we can build our ICE table with concentrations. The initial concentrations are 0.50 for N2 and 1.0 for H2. We have 0 products initially. The equilibrium concentration of N2 is 0.20 m. The change in N2 is the final minus initial, so 0.20 minus 0.50 gives negative 0.30 m. Using stoichiometry, the change in H2 is 3 times the change in N2, so 3 times negative 0.30 equals negative 0.90 m. The change in NH3 is 2 times the opposite of the change in N2, so 2 times positive 0.30 equals positive 0.60 m. We complete the table. Equilibrium concentration of H2 is 1 poabas minus 0.90, which is 0.10 m. Equilibrium concentration of NH3 is 0.0 plus 0.60, which is 0.60 m. Finally, we calculate K using our equilibrium values. K equals the concentration of NH3 squared, divided by the concentration of N2 times the concentration of H2 cubed. Substituting the equilibrium concentrations gives 0.66 squared divided by the product of 0.20 and 0.10 cubed. This calculation yields an equilibrium constant, K, of 1800. A few minutes ago, I promised a call to action. I want to invite you to connect with us at DAR Tutors for expert tuition in IB, A-Level, and IGCSE curricula. Whether you need help understanding complex concepts, developing problem-solving skills, or preparing for exams, our experienced tutors are here to provide personalized support. You can reach out to us for online and home tuition. Now let's continue with our lesson. So far, we've focused on calculating K. Now let's explore the inverse problem. Calculating equilibrium concentrations when you are given K. There are 2 main types of problems. Those where you know K and all but one equilibrium concentration, and those where you know K and only the initial concentrations. Let's tackle the first type. Consider the reaction 2COF2 is in equilibrium with CO2 plus CF4, with an equilibrium constant K of 2.0. We are told the equilibrium mixture contains 0.255 m COF2 and 0.120 m CF4, and we need to find the equilibrium concentration of CO2. This problem is straightforward. We simply substitute the known values into the equilibrium expression and solve for the unknown. First, write the equilibrium expression for K. It's the concentration of products, CO2 and CF4, divided by the concentration of the reactant, QF2 squared. Next, we rearrange the equation to solve for our target, the concentration of CO2. We get that the concentration of CO2 equals K times the concentration of COF2 squared, divided by the concentration of CF4. Finally, we plug in the given values. The concentration of CO2 is 2.0 times 0.255 squared, divided by 0.120. This calculates to an equilibrium concentration for CO2 of 1.08 m. So, when you have K and all but one equilibrium concentration, you can find the missing value through direct substitution and rearrangement. The next type of problem is more challenging. Now let's tackle the second, more intricate type of problem. Calculating equilibrium concentrations when you are given the equilibrium constant, K, and only the initial concentrations. Consider the reaction between an organic compound X and its isomer Y. We start with 1 mole of pure X in a vessel of unknown volume, V. The equilibrium constant, K, is 0.02 nari. Our goal is to calculate the amount of Y in moles that is formed at equilibrium. We will use an ice table. Let's start with the amounts in moles. Let's assume that at equilibrium, the amount of Y formed is Y moles. Due to the 1:1 stoichiometry, if Y moles of Y were produced, then Y moles of X must have reacted. The initial amount of X was 1.0 moles, so the equilibrium amount of X will be 1.0 minus Y moles. We need concentrations for our K expression. Since we don't know the volume V, we'll carry it as a variable. The equilibrium concentration of X is its amount, 1.0 minus Y, divided by the volume V. The equilibrium concentration of Y is its amount, Y divided by V. Now we substitute these into the equilibrium constant expression. The equilibrium expression is K equals concentration of Y over concentration of X. Plugging in our expressions gives K equals Y over V, divided by the quantity 1.0 minus Y over V. Notice the volume term V cancels out. This is a common and very helpful simplification when the total number of moles of gas doesn't change during the reaction, or for reactions in liquid solution where volume isn't crucial. We now have a single equation with one variable, Y. Let's solve for Y. Multiply both sides by 100 years minus Y to get 0.020 times the quantity 100 minus Y equals Y. Distribute the 0.020 and then group the terms with Y on one side. This gives us 1.y equals 0.020. Solving for Y, we find that Y is approximately 0.196 moles. We round to two significant figures, so the amount of Y formed at equilibrium is 0.020 moles. This calculation shows how using the ICE method with a variable for change allows us to find specific equilibrium amounts and concentrations. Sometimes, our ICE table calculations lead to a quadratic equation. While the IB syllabus states you won't be required to use the full quadratic formula on the exam, you should be aware of this possibility and how to simplify these problems. Let's look at an example. Suppose we have the reaction A in equilibrium with 2B. We start with 1.2 MA, and we want to find the equilibrium concentrations. We find the equilibrium constant K is 0.033. We set up our ICE table using a change of X for A and plus 2X for B, giving equilibrium concentrations of 1 minus X and 2X. Substituting these into the K expression, we get 0.033 equals 4X squared over 1.0 minus X. This would require the quadratic formula to solve for X. However, here's a key simplification. Notice the equilibrium constant, K equals 0.0033, is a very small number. A small K value means that at equilibrium there will be very little product. The reaction does not proceed very far to the right. This implies that the change in reactant concentration, X, will be very, very small compared to its initial concentration. Therefore, we can make an approximation. We assume that 1 minus X is approximately 1, because X is so small that it won't significantly change the initial concentration. This assumption simplifies the equation to 0.033 equals 4x squared over 1 plus hatas, which is much easier to solve. With this approximation, we solve for x. 4x squared equals 0.0033, so x squared is 0.0033 divided by 4, which is 0.00825. The square root of this gives x equals approximately 0.029. This is our change value. To check if our approximation was valid, we can calculate the percent ionization. 0.029 divided by the initial concentration of 1.0 times 100% is 2.9%. The 5% rule of thumb is often used, meaning if the change x is less than 5% of the initial concentration, the approximation is valid. In this case, 2.9% is less than 5%, so our approximation is acceptable. Now let's explore the deep connection between equilibrium, spontaneity, and thermodynamics. The equilibrium constant, K, is not just a number, it's a window into the energetics of a reaction. Specifically, the equilibrium constant is directly related to the standard Gibbs energy change, delta G naught, by the equation delta G naught equals minus R times T times the natural logarithm of K. Here R is the ideal gas constant and T is the absolute temperature. Remember, delta G naught is a measure of the spontaneity of a reaction under standard conditions. A negative delta G naught means the reaction is spontaneous, while a positive delta G naught means it's non-spontaneous. Because of this logarithmic relationship, small changes in delta G naught can have a huge effect on K. Let's look at the implications. If K is greater than 1, it means the equilibrium lies towards the products. For this to happen, the natural log of K must be positive. Therefore, delta G naught must be negative, indicating a spontaneous reaction. If K is less than 1, the equilibrium favors the reactants. This means the natural log of K is negative. For delta G naught to be positive, the reaction must be non-spontaneous. The reverse reaction, the formation of reactants, is spontaneous. And if K is exactly 1, the natural log of 1 is 0, so delta G naught is 0. This is the definition of equilibrium itself. The Gibbs energy is at a minimum, and there is no net tendency to move in either direction. In essence, the equilibrium constant K tells us where the reaction wants to be, and the Gibbs energy change delta G naught tells us the driving force for getting there. We can visualize the Gibbs energy relationship using energy profiles. The position of equilibrium corresponds to the minimum Gibbs energy of the system. Imagine a simple reaction A going to B. The x-axis represents the composition, from pure reactant A on the left to pure product B on the right. The y-axis is the Gibbs energy of the system. The curve represents the energy of all possible mixtures of A and B. The system will always spontaneously move towards the state of lowest Gibbs energy, which is the minimum point on this curve. This minimum corresponds to the equilibrium mixture. At this point, delta G is 0, meaning there is no tendency for the system to change. Now let's see what happens to this curve when delta G naught is positive or negative. Remember, delta G naught is the difference in Gibbs energy between the pure reactants and pure products. If delta G naught is negative, the products have a lower Gibbs energy than the reactants. The minimum point of the curve, representing equilibrium, is shifted towards the product side. This means the equilibrium mixture will contain more products than reactants. Conversely, if delta G naught is positive, the products have a higher Gibbs energy than the reactants. The minimum point of the curve is shifted towards the reactant side, meaning the equilibrium mixture will be rich in reactants. This analogy is like a ball rolling down a valley. It will settle at the lowest point, the equilibrium position, where its potential energy is minimized. The steepness and location of the valley sides depend on the sign and magnitude of delta G naught. Let's apply these thermodynamic concepts to a problem. We have a dissociation reaction carried out in a 1-to M3 sealed tube at 298 Kelvin. A graph shows the Gibbs free energy of the system as a function of the amount of nitrogen dioxide present. Our goal is to analyze this reaction and calculate its equilibrium constant and standard Gibbs energy change. First, for part A, we need to state and explain whether the forward reaction is spontaneous. The forward reaction converts N2O4 into 2NO2. Looking at the graph, the starting point, pure N2O4, is at a lower Gibbs energy than the endpoint, pure 2NO2. This means that delta G naught, the standard Gibbs energy change, is positive. A positive delta G naught signifies that the reaction is non-spontaneous under standard conditions. The reverse reaction is spontaneous. Next, part B, let's determine the equilibrium constant, K. We find the minimum point on the curve, which represents the equilibrium state. At this point, the graph shows that the amount of NO2 is 1.2 moles, and the amount of N2O4 is 0.4 moles. Since the volume of the tube is 1 dm3, these molar amounts are equal to the molar concentrations. So the equilibrium concentration of NO2 is 1.2 mm, and N2O4 is 0.4 m. The equilibrium expression is K equals NO2 concentration squared over N2O4 concentration. Plugging in our values gives 1.2 squared divided by 0.4, which calculates to an equilibrium constant K of 3.6. For part C, we use this value of K to calculate the standard Gibbs free energy change, delta G naught. We use our key thermodynamic equation. Delta G naught equals minus RT ln K. We must be careful with units. R is in joules per mol Kelvin, so our result will be in joules. The temperature is 298 Kelvin, and we just found K is 3.6. Substituting these values, we get delta G naught equals negative 8.3114 times 298 times the natural log of 3.6. The result is negative 3156 joules per mole. This seems to contradict our initial finding from the graph that delta G naught is positive. Let's re-examine the graph. The graph shows the change of Gibbs free energy for the dissociation of dinitrogen tetroxide to nitrogen dioxide, N2O4G, equal 2NO2G. For this reaction, the Gibbs energy of pure N2O4 is lower than the Gibbs energy of pure 2NO2. Therefore, djeg for this forward reaction, dissociation of N2O4, is positive, not negative. Let's adjust our calculation based on this observation. The textbook's interpretation of the diagram seems to have a typo for part A. Since pure reactants, N2O4, are at a lower Gibbs energy level than pure products, NO2, the standard Gibbs energy change, ddig, for N2O4G, 2NO2G, must be positive. Let's recalculate part C based on our correct value of K. The calculation in the textbook solution actually calculates the delta G naught for the reverse reaction, 2NO2 going to N2O4. For the forward reaction as drawn, N2O4 dissociating, delta G naught is positive 3156 joules per mole, or 3.16 kilojoules per mole. This is consistent with a non-spontaneous forward reaction and an equilibrium constant greater than 1. Therefore, for the forward dissociation, N2O4G equal 2NO2G, the correct value of djeg is positive 3.16 kJ mol 1. It's always important to carefully interpret diagrams and check for consistency. Finally, there's another important thermodynamic relationship. We can connect the equilibrium constant K directly to the standard enthalpy change, delta H naught, through an equation known as the Van't Hoff equation. This equation states that the natural logarithm of the equilibrium constant K equals the negative standard enthalpy change delta H naught divided by R times T plus the standard entropy change delta S naught divided by R. This equation is very useful. If we plot the natural logarithm of K on the y-axis against the inverse of the absolute temperature, 1T, on the x-axis, we get a straight line. The slope of this line is related to delta H naught. The slope is negative delta H naught divided by R. This means we can determine the enthalpy change of a reaction from equilibrium constant data at different temperatures. The equation also explains how K changes with temperature, which we saw earlier with Le Chatelier's principle. For an endothermic reaction, delta H naught is positive. This means the term minus delta H naught over RT is negative. As temperature T increases, the term minus delta H naught over RT becomes less negative. Since this term is being subtracted in the full delta G naught equation, delta G naught becomes more negative, and thus K increases. This is consistent with Le Chatelier's principle, where increasing the temperature of an endothermic reaction favors product formation. For an exothermic reaction, delta H naught is negative. The term minus delta H naught over RT becomes positive. As T increases, this positive term becomes smaller. Delta G naught becomes more positive, and K decreases, again matching Le Chatelier's principle. So, thermodynamics provides a quantitative explanation for these observed shifts. Let's work through an IB-style practice question to solidify our understanding. The question is, sulfur dioxide reacts with oxygen to form sulfur trioxide in a 3.0 DM3 sealed container. Initially, there are 2.0 mole of sulfur dioxide and 1.4 mole of oxygen. At 700 Kelvin, a conversion rate of 15% is achieved. Calculate the equilibrium constant K at this temperature. First, we write the balanced equation and calculate initial concentrations. The equation is 2SO2 plus O2 in equilibrium with 2SO3. The initial concentration of SO2 is 2.0 mol divided by 3.0 dm3, which is 0.667 m. The initial concentration of O2 is 1.4 mol divided by 3.0 dm3, which is 0.467 m. Next, we use the conversion rate. 15% of the limiting reactant is converted. Based on the 2:1 ratio, if we had a lot of O2, we could react all the SO2. So SO2 is the limiting reactant. The change in SO2 concentration is 15% of its initial value, which is 0.15 times 0.667 m, or 0.100 m. Since SO2 is consumed, this is a change of 0.100 m. Now we can complete our ice table. The initial concentrations are 0.67 for SO2 and 0.467 for O2. The change for SO2 is 0.100. Using the 2-1-2 stoichiometry, the change in O2 is half the change in SO2, so 0.050 m. The change in SO3 is equal to the change in SO2, so plus 0.100 m. We calculate equilibrium concentrations. SO2, 0.667, 0.100 equals 0.567 m. O2, 0.467, 0.50 equals 417 m. SO3, 0.0 plus 200 equals 0.100 m. Finally, we substitute these into the K expression. K equals SO3 squared over SO2 squared times O2. Plugging in our equilibrium values gives 0.100 squared divided by 0.567 squared times 0.417. This results in an equilibrium constant K of 0.07. Let's try another IB-style question, this one involving a quadratic solution. The reaction SO3 plus NO is in equilibrium with NO2 plus SO2. At a certain temperature, K is 6.78. The initial equimolar concentrations of SO3 and NO are 0.03 mol dm3. We need to calculate all equilibrium concentrations. We'll start by building our ice table, representing the change as X. Initial concentrations for reactants are 0.030 m. Products are initially 0. Let's assume X moles per dm3 of SO3 reacts. By 1:1 stoichiometry, X moles per dm3 of NO will also react, and X moles per dm3 of NO2 and SO2 will be formed. Now we substitute our equilibrium expressions into the K expression. K equals the product concentrations over the reactant concentrations. This gives 6.78 equals X times X divided by 0.03 minus X times 0.030 minus X. This simplifies to 6.78 equals X squared over 0.030 minus X squared. This is a quadratic equation, but a special kind. Because both the numerator and denominator are perfect squares, we can simplify by taking the square root of both sides. The square root of 6.78 is approximately 2.60. The square root of the right side is X over 0.030 minus X. Now we have a simple linear equation to solve. Multiply by the denominator to get 2.60 times 0.030 minus X equals X. Distribute the 2.60 to get 0.078 minus 2.60x equals X. Group the X terms on one side. 0.078 equals 3.60x. Solve for X equals 0.078 divided by 3.60, which is approximately 0.0217 m. Finally, we calculate the equilibrium concentrations. The concentrations of SO3 and NO are 0.030 minus 0.2 on 7, which is 0.083 m. The concentrations of NO2 and SO2 are simply X, which is 0.0217 m. Using the perfect square simplification is a key HL level skill. Here's another practice question, similar to our earlier example involving an unknown volume. An organic compound X and its isomer Y are in equilibrium. Calculate the amount of Y in moles formed at equilibrium if we start with 0.500 mole of pure X and the equilibrium constant K is 0.050. Let's call the unknown volume V. We'll follow the same procedure, starting with moles and then moving to concentrations. Our ice table for moles starts with 0.500 mole of X and 0 mole of Y. Let YE be the moles of Y formed. Due to 1:1 stoichiometry, Y moles of X are consumed. So, at equilibrium, we have 0.500 minus Y moles of X and Y moles of Y. The corresponding equilibrium concentrations are 0.500 minus Y divided by V and Y divided by V. Now we set up the equilibrium expression and solve. K equals concentration of Y over concentration of X. Plugging in our expressions gives 0.055 equals T tatais Y over V, divided by asin 0.500 minus Y over V. Again, the volume terms cancel out, leaving a simple equation. 0.50 equals Y over minus Y. Let's solve for Y. Multiply both sides by 0.500 minus Y to get 0.050 times 0.500 minus Y equals Y. Distribute the 0.052 to get 0.025 minus 0.052i equals Y. Grouping terms gives 0.25 equals 1.050i. Solving for Y, we find it's approximately 0.0238 moles. Rounding to 3 significant figures, the amount of Y formed at equilibrium is 0.0638 moles. Here is our final practice question, a more complex problem that will utilize all the skills we've developed today. We have hydrogen and carbon dioxide gas reacting to form water and carbon monoxide. The system is set up in a 10 dm3 vessel at 1200 Kelvin. We start with 2.0 mole of each reactant and 1.0 mole of each product. The equilibrium constant K is 2.10. We need to find the final equilibrium concentration of each gas. Notice we have non-zero initial concentrations of products. This means we must first determine which way the reaction will shift to reach equilibrium. We do this by calculating the reaction quotient, Q. Using the initial concentrations, Q equals 100 times 0.100 divided by 0.200 times 0.200, which is 0.25. The calculated Q of 0.25 is less than the given K of 2.10. Since Q is less than K, the reaction must shift to the right, towards the products, to reach equilibrium. This means reactants will be consumed and products will be formed. Now we can set up our ice table, being careful with the changes. Since the shift is to the right, reactants, H2 and CO2, will be consumed, so their changes are X. Products, H2O and CO, will be formed, so their changes are plus X. The equilibrium concentrations are 0.200 minus X for reactants and 0.100 plus X for products. Substitute these into the K expression. K equals 100 plus X squared divided by 200 minus X squared. This is another perfect square scenario. Taking the square root of both sides gives 1.45. The square root of 2.10 equals 0.100 plus X over 0.200 minus X. Let's solve for X. Rearranging gives 0.290 minus 1.45x equals 0.100 plus X. Grouping terms gives 0.90 equals 2.45. So X is approximately 0.0776 m. Finally, we calculate the equilibrium concentrations. For H2 and CO2, the concentration is 0.200 minus 0.0776, which is 0.1224 m. For H2O and CO, The concentration is 0.100 plus 0.0756, which is 0.1876 m. This example highlights the importance of checking the direction of shift before setting up the change line in your ICE table. Let's work through the final IB-style practice question. The question is, sulfur dioxide reacts with nitrogen monoxide to form sulfur trioxide and nitrogen dioxide. All substances are gases. Write the equilibrium expression for K. Then calculate the equilibrium constant at a temperature where the equilibrium concentrations are known to be SO2 equals 0.5020 m. No equals 0.75 m, No2 equals 0.60 m, and SO3 equals 0.45 ms. The first part of the question asks for the equilibrium expression. This is a direct application of the law of mass action. For the given reaction, K equals the concentration of nitrogen dioxide times the concentration of sulfur trioxide, divided by the concentration of sulfur dioxide times the concentration of nitrogen monoxide. Since all stoichiometric coefficients are 1, there are no powers. The second part requires us to calculate the numerical value of K using the provided equilibrium concentrations. We simply substitute the given values into our expression. K equals 0.60 times 0.45, divided by 0.50 times 0.75. The numerator is 0.270 and the denominator is 0.375. Dividing these gives an equilibrium constant, K, of 0.72. Based on this value of K, let's reflect for a moment. Since K is less than 1, what does that tell us about the position of equilibrium for this reaction? It means that at equilibrium, the mixture will contain more reactants than products. The equilibrium lies to the left. Let's quickly recap what we've learned. You should now be able to confidently work with equilibrium problems at the HL level. We started by defining the reaction quotient Q as a measure of the relative amounts of products and reactants at any point in time. We learned that comparing Q to the equilibrium constant K allows us to predict whether a reaction will shift to the right, to the left, or is already at equilibrium. This, in turn, provides a clear explanation for Le Chatelier's principle. We then saw how to solve quantitative problems using ICE tables. These tables are essential for tracking initial concentrations, changes, and final equilibrium concentrations. We practiced calculating K from equilibrium data and solving for unknown concentrations, including using the simplification for small k values and the square root method for perfect square quadratics. Finally, we explored the powerful thermodynamic relationship between the equilibrium constant K and the standard Gibbs energy change delta G naught. This equation, delta G naught equals minus RT ln K, links the spontaneity of a reaction to its equilibrium position and provides a deeper understanding of chemical change. Remember, practice is key to mastering these concepts. Review the examples we've covered and attempt the practice questions on your own. For more detailed explanations, additional worked examples, and expert tuition tailored to your needs, please contact DAR Tutors.